Halo, mana ini mahasiswa yang lain? Pak, Ramadan.
Iya, sudah saya umumin buat pukul jam 8.
Kenapa?
Sudah saya umumin buat ngumpul ke Zoom jam 8.55.
Oh, oke.
Pak Edi, Bu. Minggu kemarin itu Pak Ali gak saya kirim link Zoom-nya. Tapi
dia mungkin kalau bisa
jadi asumsikan ini
Nggak dikirim ya, Pak?
biasanya kan 1 hari sebelumnya saya kirim lagi Zoom-nya ke Pak
Terus?
Ali. Minggu kemarin kan nggak saya kirim.
Oke.
Monggo, Bu Asri.
Okay. Is my voice clear enough?
Jelas.
Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone, and welcome to our last lecture series delivered by Dr. Ali Ahmadian, hosted by Department of Mathematics, Faculty of Science and Technology, Universitas Airlangga. Today's topic is about fuzzy numerical method, fuzzy decision-making algorithm in introduction. First, let me introduce myself. My name is Asli Bekti. I will be responsible for hosting this lecture. And before Dr. Ali present his lecture, I would like to inform that the attendance list will be provided on the chat box, and make sure that you are using the virtual background provided by the committee. And if you have any questions during the presentation, just write them to the chat box and I will read them on the Q&A session. Or you can wait until the end of presentation and unmute yourself to ask directly to the speaker. Okay, Dr. Ali Ahmadian, are you ready?
Thank you, Assalamualaikum, everybody. Very good morning. And thanks. Thank you for your invitation again. And also, I hope that this fourth session can open a new window to your knowledge and makes enough motivation for you to start on focusing and working on fuzzy differential equations or fuzzy state and system in general. So before I start and continue from the previous session, I just want to introduce two important books. If anybody is interested to work on fuzzy sets and fuzzy differential equations, these two books are very comprehensive and have most of details for starting. So let me share my screen and what we have. Okay, so the first one is a fuzzy differential equation in various approaches. This book published by Springer and discuss about different approach exists for fuzzy differential equation, including different fuzzy derivatives, differentiability, and so on. So this one is the first one, and the next one also. So just pay attention that this book, the authors are Luciano Takata, Reggio, Carvalho, De Burris. This is the second and third one. Barnabas Bede are very famous guys in the fuzzy differential equations. And the next book is the mathematics of fuzzy sets and fuzzy logic. Again, it has a single author, Barnabas Bede. It discusses about the fuzzy sets, the operations, fuzzy relation, fuzzy number, arithmetic, and in this part go to the fuzzy differential equations and so fuzzy transform, so on. These two books are interesting and has some good or enough knowledge about fuzzy if you want to start to work on fuzzy and then fuzzy differential equation. One more book published by the same author, Barnabas Bede. You can find it published, I think that in 2015 or something, same publisher Springer. Also that one published by this guy, Barnabas Bede, discuss about fuzzy differential equation and also more important, the characterization theorems and also the derivatives. We call a type of derivative fuzzy generalized differentiability. So just these three books, this one, another one, different approach on fuzzy differential equation, and last one, as I told you, similar book published by same author, Barnabas Bede. These three books, if you as a senior undergraduate student, or you as a junior postgraduate student wants to work on fuzzy, not only for the master, but also PhD. So these one give you a very comprehensive, detailed, and useful information for fuzzy sets and fuzzy differential equation. Then you have enough good knowledge to start to work on fuzzy differential equation and also numerical methods, or if you want to develop to other type of differential equation like fractional differential equation, delay differential equation, impulsive differential equation, or random ones. So anyway, these books are helpful. That's why I prefer that first to give you these ones for anybody who is interested to work. So the next thing that I wanted to share that I think that Mr. Mohammedian has my email, and yep. So anyone who is interested to work or make collaboration or I don't know for continuing the study on in this area, he or she can contact me. Then if so we can make some meetings or discussions time, and I can share also my WhatsApp number, so to help you or collaborate with you in any way you want. So this is what else I wanted to share. Anybody is interested can refer to Mr. Mohammedian for my email and contact information. So thanks. Okay. Let's start to continue with from the previous session. Today we will discuss about this is my laptop cable makes problem. Okay, today we want to discuss about the fuzzy differentiability, fuzzy differential equation, and then go through the numerical parts. I try to give you a brief approach to the numerical part. It's important because sometimes I think that the first session I show you that some articles they try to use the numerical methods for fuzzy differential equations, but totally wrong because the theory has not been established perfectly. Last thing is that yes, sorry, I forgot to share my slides. After the session, I will send my slides to Mr. Mohammedian, so he will share with you for anybody who wants. And so this is what I wanted to tell you. And let's start to see that what we have. Okay. Up here. So we reach to the difference of fuzzy numbers. Here, this is the last part. The fuzzy numbers. We have the most common difference for this number is called Fukuhara difference. It's defined by this symbol. So this is this notation stands for Fukuhara difference. And why we have this, the necessity to have this difference compared with the normal one, because if I told you, if we follow the Zade extension principle, then using this one, we want to transfer, if we assume that the difference of two fuzzy number as a function, and I want to find the output of this function, the difference, under Zade extension principle, means that I want to fuzzify this operation under Zade extension principle. Then we found that under this principle, u minus u, if u is a fuzzy number, is not equal 0. So this is the problem for difference of subtraction of two fuzzy number, or so we know that in the classical mathematics, anybody. So if we have two numbers, u minus u should be equal 0. While if we want to consider this is as an operator function, we want to do this difference over a fuzzy number, then we found that it's not equal 0. You can refer to the detail of why we have these things, why we reach to this inequality. So I remove here the details you can find in these 3 books that I discussed, I introduced to you. So anyway, because of this problem, in 1987, proposed the Puri and Ronsky proposed this difference that remove the shortcoming appeared here. So it is in fact already proposed, this Fukuhara difference, already proposed by a guy named Fukuhara in a long time before that. So I think that 1910 or something like this. But these guys extend the concept for fuzzy difference, considering the fact that we have u minus, it's a Fukuhara minus Fukuhara v is equal w if and only if u is equal v plus w. This is addition, is a standard fuzzy addition, means that if we have 2 fuzzy numbers, I wrote it here, we have 2 fuzzy numbers, then this summation is the standard fuzzy number that you need to add element by element. 2 plus 3 is a 5, 3 plus 4 is 7, 4 plus 5 is 9. It's a standard fuzzy addition. So this definition say that if we have a Fukuhara difference, then u minus Fukuhara v is equal w if and only if u is equal v plus w. Considering this relation or this new concept, then we do not have this shortcoming. So we know that u Fukuhara difference u is equal 0. 0 is a fuzzy, 0 fuzzy number. So then what's interesting here, in classical operations that we have, what we have here, we, for example, assume that we have 2 vectors, okay? Vector 1 is A1, A2, A3, okay? And vector 2 is a V, is B1, B2, B3, okay? I want to make a difference. All of you know that what we can do is it's an U minus V is equal, what we have is A1 minus B3, correct? And then we have A2 minus B2 and A3 minus B1. This is what we have in classical mathematics. But we know that if we want to consider this difference, that's why I want to insist on this part, because most of problems, most of wrong theories started from this part in the articles. And I insist on the fact that if you want to work on the fuzzy differential equation, you should perfectly understand the concept of fuzzy Fukuhara difference, fuzzy generalized differentiability, and so these different differentiability that are based on this Fukuhara difference. Otherwise, your outputs will be wrong. I just want to explain this part, that in classical mathematics, we have u minus v, you can see. But once we want to have the Hukara difference, you can see that this is the alpha cut, okay? The alpha cut is what we have, means that what we have is the u alpha is the, we know that, just have a, we want to recall, okay? So u lower means that for the left side we discussed, and also u upper for the alpha cut. For v alpha cut, we have v lower alpha and v upper alpha. Then I want to find the Hukara difference of u v with alpha. You can see that what we have here is the difference is not like this one, that we change the order of the components we have. We have in the Hukara difference u alpha lower minus v alpha lower, u alpha plus or upper minus v alpha plus or upper. You can see that we don't change the order. This is the difference between the classical subtraction and fuzzy subtraction based on Hukara concept. And now you can easily verify using this notation that u Hukara difference u is equal 0. You can see that I consider an alpha cut, u Hukara u, sorry more for my handwriting. And so what we have, the lower one minus lower one, u alpha minus lower u alpha, and the upper bound minus upper bound, u plus alpha minus u plus alpha. Then this is equal 0, and this is equal 0. So what we have, 0 and 0 alpha, what we saw means that it's the 0 alpha, which is equal 0. So you can see that if we use Hukara difference, then we do not have any problem. One more thing that last session I one of you asked, that these are the same concept, just different notation. So for the left side, you maybe see that v lower, you maybe see that v lower, you maybe see that what we have, what else? For example, v1 maybe. For the upper one, you maybe see this one. You maybe see this one, or you maybe see this one. All of these, this one for lower bound, this one for upper bound, same concept, just we use different notations. Okay, don't so it's not confusing. Just we change in notation. Why I put, for example, the lower with the minus or so under bar, and here I consider a right side a minus thing, while for the left side minus thing, while for the right side I use the plus notation. But generally all are same concept, just different notation. So you found that what's the meaning of Hukara difference? At first I wanted to give you this approach. Okay, if you see the difference, maybe later we have other definition, but the most important one we have this one. Then in the 2009, another revision of deep definition proposed by these two guys, Stephanie Bede, okay? They propose a new approach, not a new approach, a revised type. So call that GH difference, means that generalized Hukuhara difference. What this says, it says that if we have U minus generalized Hukuhara or GH, V equal W, if and only if we have one of these types. So the first one, what we have? The first one is the Hukuhara difference. So the first one means that if we have U minus GHB equal W, if and only if one of these situations happen. The first one is the Hukuhara difference, or B is equal U minus W. Means that if we have one of these situations, U is equal V plus W, or V equal U minus. This minus is the standard difference, okay? Then if and only if we have U minus or general difference of generalized Hukuhara, V equal W. This is another common difference that we have. So what it tells in practice, like this one we have here, U minus Hukuhara, V is equal this one. Then how about this one? This one in practice say that if we have the alpha cut of U minus generalized Hukuhara difference, V also equal the minimum of U lower minus V lower, U plus minus V plus, and the maximum for U minus minus V minus and U plus minus V plus. What it tells? It tells us that if we want to make a difference of these two fuzzy numbers under generalized Hukuhara difference, then at first you make a difference lower bound minus lower bound, upper one minus upper one. Okay, then the minimum between these two differences we consider as the left one, and the maximum one considered as a right one. This is the difference, the generalized Hukuhara difference of two fuzzy number based on alpha cut. This is the general definition, the general frame of the difference. But while we want to work on the alpha cut, we consider, in fact, in practice, this proposition. And in the numerical part, I will show you that if you want to consider only the Hukuhara difference with some models that we have, like this model, like Y prime equal a very simple model, lambda Y, that lambda is less than 0. Then if we use Hukuhara difference, so we have a divergence in our numerical method or exact solution, and we tell that on that situation, if we use Hukuhara difference for this type of differential equation, or make it clear, this is for multiplication, okay? The fuzzy multiplication, Y prime, I make it more expanded form. So if we consider the generalized Hukuhara difference or generalized Hukuhara differentiability for this simple fuzzy ODE, then over a time interval or in uncertainty is increasing. we want to have some solutions for output of such differential equation that has less uncertainty. But I will explain once we have a type of these differential equations and over a time interval using a fuzzy Ukora differentiability, we have more uncertainty. Just a point in your mind, please keep it. We will describe. So now at this point, this is the definitions we call generalized Ukora differentiability. Again, if you refer to the book, talk about different approach of fuzzy differential equations. One of the approach is based on this definition. Then then again they proposed another type of difference they call G difference or generalized difference. The generalized difference is the support of union of the alpha cuts of two fuzzy numbers, but in fact, again, in practice, this is the general. The notation, in fact, is different from, this is what we have is generalized Ukora difference, but this is the notation for generalized difference, okay? But in fact, what it is, it want to tell us, that if we have a difference based on the generalized difference, then compare with the generalized Ukora difference. For generalized Ukora difference, we consider the minimum of the difference of left and right bond, and put it at the left side, and the maximum of this difference, I put it on the right side. But generalized difference, they tell that we need to consider the infimum of the minimum of these subtractions, considering this infimum should be for all of the B or beta cuts greater or equal alpha, and supremum are all beta cuts greater or equal alpha. It tell us that. What it tell? So it tell us that if we have an alpha cut of two fuzzy numbers, then any beta cuts greater than these alpha cuts, any beta cuts that greater than these alpha cuts, we consider the union of these beta cuts, and then the infimum and supremum of these beta cuts we consider as the left and right side. I don't want to confuse your mind. Just keep in your mind that we have this definition for G difference. Still in the theories that researchers are trying to discuss, give some differential equation based on G difference. But if I, as a student, want to work on numerical methods or differential equations and using numerical method for solving, I should use the Ukora difference and also generalized Ukora difference. Still is not very common for numerical parts to use this difference, generalized difference, okay? What we have here, the example, I passed this example because make it confusing for you. So metric spaces of fuzzy numbers. If you read the book, textbooks of fuzzy, if you read the fuzzy articles, at the beginning or preliminary part, you can see that the authors propose a space, they call it a Hausdorff space, and then this Hausdorff space has a Hausdorff distance. And then they tell that we have this Hausdorff distance for fuzzy number. But the important thing is that what is this Hausdorff distance that we try to define as a metric for our fuzzy number? Okay, just have a look, because we do not want to go to the algebraic details or functional analysis. So we just want to say that if we have two fuzzy numbers, okay, these fuzzy numbers, we have for example, the alpha cuts. Then under the Hausdorff distance tell us that the distance is the maximum of absolute error, or A1 minus B1 and A2 minus B2. If let's assume that we have A as the alpha cut of a fuzzy number and B alpha cut of a fuzzy number, important definition here is that Hausdorff distance is defined of maximum of absolute error, absolute fuzzy, the difference of these two intervals, the lower ones and the upper ones. This is we call Hausdorff distance. So the more expanded definitions tell us that you can see in most of fuzzy differential equation articles and textbooks. Tells of we have the Hausdorff distance between two fuzzy numbers. We usually show it by d here, and it is supremum over all alpha cut or r cuts, no difference, just different notation. Okay, supremum of maximum of the subtraction of lower bound and upper one. Subtraction of these ones, we call that the Hausdorff distance, or supremum, referring to here, supremum of DHURVR. This is what we define Hausdorff distance and between fuzzy numbers. If we want to find tell us that the metric space that is used for fuzzy numbers is called Hausdorff, then we know that the distance is defined based on this definition: supremum of the r cuts over the maximum of the subtraction of lower and upper bonds. So it has some properties like the du plus c. If we have three fuzzy numbers, du plus w and v plus w is equal duv. Or if we have the multiplication of a constant, arbitrary constant belongs to real number line, so k dot u, k dot v is equal the absolute value of k d Hausdorff distance uv. And the last one is also the inequality holds for the Hausdorff distance. This is three important property of Hausdorff distance. And so yeah, we have here LP distance also for fuzzy numbers, defined like what we have in the classical mathematics. This is we just replace for dp referring to LP distance. So it's the integration from 0 to 1 for the Hausdorff distance. Okay, and yeah, normal fuzzy number. The normal fuzzy number, in fact, is equal. Now you can see we have the different definition of the Hausdorff distance. Norm of a fuzzy number is equal the Hausdorff distance. So then under this definition, we know that the norm is equal 0 if the fuzzy number is a 0 fuzzy number. And also we have other properties. So And what we have here at pass, we have the integration. For the integration, then we have fuzzy integration. It tells us, this definition tells us if we have a fuzzy function, which is integrable, okay? And we want to define the fuzzy integral. So if the norm of this fuzzy function is less than a function, an arbitrary function defined over or Hausdorff distance, then we can have the R cut of a fuzzy, the integration of a fuzzy function, so is equal, we can insert the R cut under the fuzzy integration. So it means that we can get a normal integration. So we insert the R cut insert over the function, fuzzy function. We have then non-fuzzy or crisp one, and then we can get the integration. It's not very complicated. Just we should care that the norm is bounded. It's telling this definition that if or the norm of fuzzy function is bounded, then satisfied to get the fuzzy integration and also fuzzy Riemann integral. What we have here, we usually show it by this notation, considering some condition for fuzzy Riemann integral. So Henstock integral is not important. Yeah, this the proposition is important, that maybe in the textbook you can see that the concept of Amman integral, Riemann integral, and Henstock integral. If I just want to give you an important proposition that all these definitions, fuzzy Riemann, fuzzy Henstock, fuzzy Amman, so these are actually equal if we have a continuous fuzzy function. They are actually equal. And the next thing which is interesting about the properties of the integration of fuzzy, if we have fuzzy function, then you can see that we can easily separate them. There is not any restriction. Okay, and sorry, if we have an interval for our function, or domain of fuzzy function is defined from A to B, a closed interval, then we can divide it to find a midpoint, then considering the integration till this midpoint, and then from this midpoint up to the end. It is actually equal with the integration over the whole of the interval. So this is another property like what we have in the classical mathematics or calculus. And so the last one is this one. If C belongs to the fuzzy numbers, the space of fuzzy number, please pay attention. If C belongs to the space of fuzzy number, this one stands for the space of fuzzy numbers. And F has constant sign, means that doesn't change the sign over the interval. So it is a fuzzy function, has a constant sign, not like this one. For example, this one we have a change in sign, it doesn't hold. If we have constant sign over the interval, then see the multiplication by F, this is stand on fuzzy multiplication. Depend on which definition you select for the fuzzy multiplication, we can take it out and then get the integration. This is the last property of fuzzy integral. I pass the green function, differentiability of the fuzzy numbers. We talk about fuzzy difference. I just check that any, okay, I thought that there is any question. We have fuzzy difference. We already talked. Fuzzy difference is based on fuzzy Hukawara difference, fuzzy Hukawara generalized difference, and fuzzy generalized difference. The three common ones. Now, we want to define. At first, have a look on the definition of differentiability in calculus. This one tells us if we want to get the differentiability, it means that like limit of at the point, for example, x tends to x naught, then what we have fx minus f naught, x minus x naught, point x naught, okay? Or what we have, f prime x is, we have the limit h tends to 0, fx plus h minus fx, correct, over h. These are the definition of the differentiability we have. But the problem is that if we want to develop this concept for the fuzzy differentiability, then what we should do for this notation? What we can do for this one? Based on this difference, we can use fuzzy Hukawara differentiability, or fuzzy generalized Hukawara differentiability, or fuzzy generalized differentiability, depending on which difference we select. The first one is that referring to the Hukawara difference, we use this Hukawara difference, and the output is the Hukawara derivative. Why it is Hukawara derivative? We call it Hukawara derivative because we use this Hukawara difference. Based on this one, a guy in 1987, Stekala, proposed the derivative based on Arcots. Tell us that the Stekala, so it's with his name, or Hukawara derivative or Stekala derivative of a fuzzy number is defined like this one: f prime x over the Arcot or alpha cot is the left side prime and right side prime, provided that it defines a fuzzy number f prime. Arcot between 0 and 1. It calls Stekala derivative. I just want to ask you to have a look on the derivative. You can see that because this is the theoretical frame. We usually also in calculus, we do not work with the theoretical frame. We employ the practical one. So this is the theory, but in practice, the Stekala derivative or Hukawara differentiability or Hukawara derivative is defined like this one: the Arcot or alpha cot of the f prime provided that this f prime is a fuzzy number. Why such detail is important, provided that it defines a fuzzy number. So maybe it is a very simple direction to the definition, provided that it defines a fuzzy number. Okay, so what's the matter? We are sure that it's a fuzzy number. But let's make a pause here, and then I want to give you importance of some things which are maybe not very necessary. Yep, here should be, okay. Let me download a fuzzy, put it here. And I want to show you that some things which are maybe not very important, but make it very important. Yeah, okay, let me share my slide now. Here. So this is the, I just have this is an article I published in 2018, okay? Numerical solution of a fuzzy differential equation by an efficient Runge-Kutta method with the generalized differentiability. There you can see that it was published in the fuzzy set and system. But the important thing is that once we go through, you can see that we start with some basic definitions, like what we have about the support, what the properties of a fuzzy number, and the Hausdorff distance, what I just explained. Here, we explain that we have a generalized Fukuhara difference, and then the differentiability here is defined based on Fukuhara differentiability. Then I go through the generalized Fukuhara differentiability, explain it. The problem is that in one of the part of my discretization of the numerical solution, so after several passing review time, so one of the reviewers told me that I want to reject your article after several review time. So because you did not give us the point that why we should accept your solution as a fuzzy number, why I should consider the output of your numerical method based on Runge-Kutta method. You know that very famous method Runge-Kutta in OD. I developed a type of Runge-Kutta for the numerical part of differentiability. Then he wanted, after several review, wanted to reject and told me that I could not find any evidence of your output is a fuzzy number. I was confused on that part. What it tells, I give a plot to show that my output is a fuzzy, triangular fuzzy number, and then my output is showing that everything details is correct, everything under generalized Fukuhara differentiability and so on. Then I found, once I review and confused, that what I should add to the theory, to the numerical part, to convince the reviewer that my output is correct. I'm talking about 4 years ago, not very long time. I reached the fact that Seikala and also Bede in the definitions mention that if you follow the secular derivative or use secular derivative, then you should ensure that f prime is a fuzzy number. So then I refer to the secular and demonstrate in the revision that my f prime is a fuzzy number, then outputs of the f prime also fuzzy number. Otherwise, the secular derivatives doesn't hold. I refer to this definition and also another definition by Bede, published in 2009. Then he mentioned that, okay, now it's convincing and I accept the article. I want to tell you that some very unnecessary at the first sight, unnecessary thing maybe makes maybe makes some important output. So once its definition tells us the secular derivative of a fuzzy number value function is defined like f prime, provided that it defines a fuzzy number, means that the f prime, you should ensure that your f prime is a fuzzy number. Then you can do the secular derivative, that getting the derivative from left side and the right side, and so you have the secular derivative easily. You can see that if you make a fuzzy function, get the alpha cut or R cut, then the left and right give you a secular derivative. But the problem is that the secular or Hukawara differentiable has a problem. In some cases only. What is the problem? I want to expand this definition for the secular or for the Hukawara differentiability in general. The left side, f minus r, the alpha cut x plus h, minus f minus, I just expanded, x over h, the limit, and also same for the right side. The problem is that if you use secular differentiability, then the length of the function, f means that f plus the lower minus upper, okay? So the lower minus upper is equal or greater than 0. Then using the Hukawara differentiability over the time interval, I already mentioned you that we have some problem. That's why we should switch to the generalized Hukawara differentiability. In some cases, by increasing the time, these lengths increases. Then we have, for example, if we consider, you can see this is the output under Hukawara differentiability. Okay, I got the numerical or exact solution, anything. So over the time interval between only I don't know, between a very small part. So I think that referring to the description, maybe the figure 1. Figure 1, so display the approximate solution. Yeah, so under differential at t equal 1, I have the solution of a simple fuzzy differential equation under Hukawara differentiability at t equal 1 for the left side. You can see that only t equal 1. We have a wide output from -40 up to 30 for our triangular fuzzy number solution using Hukawara differentiability. But if I use generalized two-quarter differentiability, then you can see that the length means that the difference between left and right of the fuzzy number, okay? You can see the length here and compare it with the length here. Very wide lengths once we use two-quarter difference, and very tiny or small lengths once we use generalized two-quarter difference. We want to include that if in some cases, what is this case that we have this problem? I think that, yes, this is the fuzzy ordinary differential equation, and multiplying, you can see multiplying by a fuzzy number, a negative fuzzy number. I asked you previous session that search and find, tell me that what is the meaning of positive fuzzy number and negative fuzzy number. Because of this one, in numerical part or any other theorem related to the differential equation, this is the negative fuzzy number. If the right side of the equation multiplied by negative fuzzy number, then the output, we had a very wide length, increasing, or tell us we have an increased value for uncertainty. We want to control the uncertainty using the two-quarter differentiability. Once we have fuzzy negative, the negative fuzzy number here, the negative fuzzy number, so we have very wide lengths of fuzzy solution for output, while if we use the generalized, we have, so we do not have such problem. So because of these links, we prefer for some cases to switch to the fuzzy generalized differentiability. Then before that, we have a proposition tell us, because to avoid this problem for secular or two-quarter differentiable, we have a proposition say that a secular differentiable function has a non-decreasing length of the closure of the support. A secular differential function has non-decreasing length of the closure of the support. If we have non-decreasing, we have a function as non-decreasing length, then we can employ secular. In other cases, we should switch to the generalized two-quarter and cannot use two-quarter differentiability or secular differentiability. Like what we have, for example, if we have f equal xt, yt, zt, a triangular fuzzy function, then the two-quarter differentiability for this one is a x prime, y prime, z prime. Okay? Then assume that this f is equal minus et, z, 0, and et. Then f prime, what is f prime? So we get the derivative one by one. Will be what we have. We have minus et, 0, and et. So f prime is equal f. But also f prime is equal minus f. You can see that f prime is equal minus f. For another case, we have a triangular fuzzy number multiplying by e to the power of minus t. F is suppose that it's differentiable, then f prime is minus e minus t minus 2 e to the power of minus t and minus 3 minus e to the power of minus t. It is not a fuzzy number. Provided that it defines a fuzzy number for f prime. it is not a fuzzy number. Please, because I cannot discuss more on this interesting topic, please, if you're interested, read more details of what's happening. If you get what's happening about fuzzy differentiability, then and fuzzy number, so operation, then I can tell you half of the concept, you got it. So because of the problem related to the lengths I describe here also in the article, so we go through the defining generalized differentiability based on generalized Fukuhara difference. To remove the problem that I discussed. This definition tell us that compare it with the previous definition. The first option is the Fukuhara, same as Fukuhara. This is the revision of the Fukuhara differentiability. Just add some more thing. These 4 cases that the generalized differentiability give us. First, 2, third, 4. So these 2, 3, and 4 are not very popular because the output is not fuzzy. I don't want to discuss why. So, but this one, the first 2 are important. Using the generalized difference that we reach to the generalized differentiability. The first one is the Fukuhara one. So one, because we use what we have, I just want to refer you to the generalized Fukuhara difference. Okay, generalized Fukuhara difference tell us, if I find it should be here, I think. Yeah. So generalized Fukuhara difference compared with the Fukuhara difference give us only another option, because this one already exists in the Fukuhara difference. Generalized Fukuhara difference is trying to give another option. Same for the generalized differentiability. So it's trying to give us another option. While the previous option, still we have it. Don't need to change. We still have this one as the option 1. Then the generalized differentiability add these 3 options. Number 3, number 4 are not very usable. It's using while we have switching point. I don't want to go to what the meaning of switching point and so on. So the second case is for our problem, to prevent the wide lengths of our fuzzy number for output of fuzzy function. We add this one. We'll see that in the examples of how it works. So I pass here the concept of weakly generalized differentiable and strongly generalized differentiable. I refer you to check it, because it's important. While the notation of generalized Fukuhara derivative, we usually use this notation, GH, you know that. But for the F prime, we use GH, means that once we have F prime with GH, means that we have fuzzy generalized Fukuhara function. And so it is the notation for it. So some details here, because we have a limitation of the time. I pass it here, the equivalence of the generalized derivative and generalized Fukuhara derivative. So what they are actually, they are equal under some condition. in numerical methods, we usually use the generalized Hukawara differentiability, and Hukawara differentiability, we do not use generalized differentiability. So I pass here to important things which are required for the, we want to go through the numerical parts. And yeah, we have, if we have the, you can see that we have the fuzzy value function. It is actually not generalized Hukawara differentiable, but it is generalized differentiable. I don't want to confuse you. You can, after understanding perfectly the meaning of the Hukawara differentiability, the meaning of the generalized Hukawara differentiability, then you can go through the details why we need to have the generalized differentiability or G differentiability. Why we need to have it. What are the cases number 3 and number 4 in the generalized Hukawara differentiability? I told you that case number 3 and number 4 are for switching points. What is the meaning of switching point? I don't want to give you some description of the switching point because it's make it difficult for you. Then you tell that, oh, stop, I am confused. I prefer to don't go through the fuzzy differential equation because maybe it's too difficult. Why? It's not actually too difficult. It has, depending on the level that I want to work. Maybe I am a student, I want to work on the numerical part. So, okay, then in this case, the generalized differentiability and generalized Hukawara differentiability and Hukawara differentiability is pretty enough for me. I just want to go through the detail of discretization of the numerical method. But if I want to develop new concept for the theory of fuzzy differential equation, yes, then I need to have knowledge about the G difference or generalized difference and generalized differentiability and so on, depending on the level that you want to work. For example, here, I provided an example. So ask you to prove that it is generalized differentiable, but it's not generalized Hukawara differentiable. So I pass here and we go through the fuzzy differential equations. Once let me check at first this, yeah, as Dr. Asri mentioned that if you have any question, please share in the chat box. Any question regarding the fuzzy concept, fuzzy set, fuzzy differential equation, please write in the chat box. At the end of this session, I refer to the chat box and try to answer all of your questions, so don't worry about it. I want to go through the fuzzy differential equations. We have because we have fuzzy fuzzy Hukawara differentiability and fuzzy generalized Hukawara differentiability, then depending on which type of differentiability I use, my fuzzy differential equation is defined based on that. Okay, so if I select a fuzzy differential equation based on the fuzzy Hukawara differentiability, then I follow this one. Follow first characterization theorem. It is important because the details so you can read it later and see that what are the conditions. The output is important. This characterization theorem says that if we have a fuzzy function, get it the R cut of this fuzzy function, the left side and right side. we show the left side with the minus, right side with the plus. Okay, under some conditions, I don't want to go through the details of the condition. Under some conditions, we have fuzzy initial value problem, or FIVP. We show it by x prime is equal f t and x, means that the right sides are the functions of t and x, left side is x prime. It has a unique solution if we characterize this fuzzy differential equation based on a system of two ODEs. It is very important. It tells us, this is, we call it first characterization theorem, okay? What it tells us, it tells us that if we have a fuzzy function, it is continuous, then we define a fuzzy initial value problem. Means that why it is initial value problem? Because we have initial condition. X t naught is equal x naught, x prime t is equal f tx. We know that f is a fuzzy function. Here, the left side and right side you can see. Then I cannot work with the fuzzy differential equation or fuzzy initial value problem directly. Again, I should transfer it to the non-fuzzy area. Do my computations, anything, getting exact solution, numerical solution, anything. Then again, back to the fuzzy differential equation or fuzzy initial value problem. How? The first characterization theorem tell me that you should consider the left side as the two, so the alpha cuts or r cuts of the left side, x minus r prime, x plus this is r, and then we have f lower, so we write it with r, and f plus. The theorem tell me that if you have the r cuts of this right and left, then if you want to solve it, you should solve in an ODE system, while the first equation of the ODE is the lower r prime equal lower f. And the second one is the upper r prime is equal upper. This is lower. Let me show it with the different here color. Lower, this is upper. Under characterization theorem means that we should check some conditions. So to decide the details, tell me that, for example, I have a fuzzy initial value problem like x prime is equal fuzzy, what we have, fuzzy function like -1, 0, 1, and x. Then the initial condition x at 0 is equal 2, 3, 4. Okay, for example. Then the characterization theorem tell me that if you want to work with this fuzzy initial value problem, you should transfer it to an ODE system, which is the left side is that the first equation. I just want to write the left side, x prime r, for example, lower equal. this fuzzy number, I should write the alpha cut. Alpha cut is this one minus 1 plus alpha, 1 minus alpha, or because I want to make it union, minus 1 plus r, 1 minus r. This is the r cut of this fuzzy number. I should write minus 1 plus r x lower r and x prime, the upper one, r is equal 1 minus r x upper. I have two equations, an ODE system that now I can solve it exactly similar to what we do in the calculus. If you want to work on the numerical part, you can do. If you want to get the exact solution, you can do. Any way that you select to solve in the crisp or non-fuzzy, you can start to do it. Similar, no difference, because under characterization theorem and considering the fact that we have Hukawara differentiability, so we transfer it to an ODE system and then we can solve it. Like an example here, in the example what we have is the x prime is equal minus x plus 2e to the power of minus t minus 1, 0, 1. X naught is minus 1, 0, 1. You should check the condition and so on, okay? So, but the issue is that I want to solve this one under the form of an ODE. We ignore this part because it's not usable for us. The left is minus x. Please pay attention to the what we have here compared with this example. Minus x. What we can write, we should write it x prime lower, and what we have r cut or anything, so r cut x prime upper, and then it's equal minus x. If I write as an alpha cut minus x or r cut, so it's x lower, x upper, r here, okay? Then this example did not tell me that this minus here is the Hukawara difference, because we know that the Hukawara difference, in Hukawara difference, we don't change the side of the interval. So means that this one is standard. Multiplying minus here, what we have, minus xr is equal minus x upper r minus x lower r plus 2e minus t. We can write minus, for this one, you know that minus 1, 0, 1 is equal minus 1 plus r. I just wrote it 1 minus r. Then I want to write the system. Please pay attention how I write it. It is the core of, if I want to develop any numerical method under Hukawara differentiability, I should follow this way as the first step. Then I go through the numerical part. So I write it x, the left side, x prime lower r to e minus t minus 1 plus alpha. X prime upper 1 r 2 e minus t 1 minus r. Sorry, here I wrote alpha, it's actually r. Okay. What I should write here? Left, what we have in right, we have for this one. Minus xr, or r cut is minus x upper r minus x lower r. If I want to write, I should write minus x upper r minus x lower. This is the two equations, ODE, to make our system. Then we should start to solve it. And please pay attention that you can now behave like what we have. For example, how you solve x is equal minus y plus 2e minus t something, and then x is equal y plus 2e to the power of minus t. Sorry, this part is like, yeah, this part is x equal minus y plus 2e to the power, for example, y, we have y equal minus x plus 2e to the power of minus t. For example, like this one. Exactly. So don't confuse yourself with the lower and upper. We are now in the non-fuzzy area, and we want to solve this system. Like how we solve an ODE system, we should solve this one. If you solve it exactly like what we have in calculus, then we reach to the solution like this one, e to the power of minus t minus 2e to the power of t. Here we continue, because we continue based on the r cut, or solution is based on r cut, something based on r cuts. So, but if we continue based on the approach of considering the center and left and right, then the output is a fuzzy number. Again, you can see that the example here wanted to show that we transfer a fuzzy initial value problem to an ODE system, then we solve it based on exact solution method, based on numerical method, anything. Then output, again, once you return, you have a fuzzy number. If we consider the condition of this theorem, we call it the first characterization theorem that we have. This is the first step of your way to developing numerical method for solving fuzzy ordinary differential equations. The first step. That's why I insist on details of fuzzy difference, fuzzy Hukawara differentiability, fuzzy generalized differentiability, and then now characterization theorem. Because if you understand the characterization theorem and these differentiabilities, then you can develop correctly your method, numerical method for fuzzy differential equation. But if you don't understand these concepts, which are foundation of the fuzzy differential equation, give you the tools of working with fuzzy differential equation. If you cannot understand perfectly the theory beyond this problem, then your output, your article will be wrong, like what we have currently, several articles published in even good journals, because I'm sure that the researchers did not read perfectly the literature review and made this problem. So that's why I asked you to focus on the characterization theorem, read the textbook that I introduced at the beginning of the session about fuzzy differential equation. Then I'm sure that you can develop numerical methods, theory about fuzzy differential equation, and so on. A lot of material still here. I could not reach to them because we are at the end of session 4, while I will share with Mr. Ahmadian. And so if you are interested, you can collect the slide. But if you want to start to work on fuzzy differential equation, which is a very wide area with very hot topics, makes novel output, so you should start considering the textbook that I share. And if you have any problem, so you can contact me using yes, al@keem.edu, or this my another email is the Ahmadian. This is A, okay, dot Hosseini, HOSSEINI at unirch.it. So that's it. So IT, unirch.it. So you can refer to me or contact me using this email, and I will try to answer you as soon as possible, or so make some discussion meeting or anything. So I think that if you focus, you are in a very near future, we will have so interesting output from this university, and make all of us delightful. Thanks for your attention during this 4 sessions, and thanks again the department for your invitation. And so I hope that we have something more in the future for collaboration and finding common points for making interesting and high novel outputs. So now I stop sharing, and now it's open for any question, comment from the audience, please. Thanks.
Okay, thank you, Dr. Ali. Interesting explanation about the fuzzy, especially in fuzzy ordinary ODE, right?
Yes,
okay. Now we come to question and answer session. Is there any question from the participants? Okay, Doctor, we have already MATLAB software to obtain the solution of ODE. And how about the fuzzy ODE? I mean, is there any modules or software that we can use to obtain the solution?
Yeah, still you can, because actually we work with the ODE system, as I just explained, for fuzzy ODE, same for fuzzy partial differential equation, same for fractional, no matter. So because we transfer to the non-fuzzy, again, we can write our codes in MATLAB. We do not need any extra toolbox, unless if you want to work on fuzzy simulation, then you can use Simulink in a MATLAB, and so it's different story. But for the differential equation, we do not need any extra software. We can use still MATLAB for solving and writing the codes.
Okay, thank you. So we can use the ODE 45 or ODE 23?
No. ODE 45, ODE 40, or other type of ODE function is usually for give you the crisp solution for or non-fuzzy solution, the algorithm is based on the type of Reggio and so on. It's not suitable for the discretization of or fuzzy, because in fuzzy we have the alpha cuts or R cuts in the output of ODE system. So the R cuts can be some values between 0 and 1. So we should check it. We should make a loop for this R cut. So it's not possible for ODE 45 or some other type of this function. That's why I mean that we can write our codes if we want to implement using, for example, like what I share with you, the numerical method for Reggio method, my article. So we wrote the code in the MATLAB, but we have not used ODE 45 because it has a crease design for crease. We have some R cut. So it's different. If any students is interested to work on the fuzzy differential equation, then on that time, we can share the more details, how we should make the discretization, how we should run the method, and also possible sharing the codes for him to be familiar with writing the codes in the MATLAB.
Okay, thank you, Doctor. Okay, and for the best participant, is there any questions? No one? Okay, Mr. Muhammadan.
Oh, saya tapi minta ditranslate, Bu.
Oh.
Belum buka Google Translate kan.
Ya jadi, Pak.
Pakai bahasa Indonesia dong.
I can understand a bit Malay, but not very much, not very developed. But
okay, anyone? Okay, I guess there is no more questions. And since today is our last series, okay, Dr. Ali, is there anything else you would like to mention?
Again, I ask students that if they are interested in working on fuzzy differential equations, because I still have not seen any significant efforts from Indonesia regarding the fuzzy concept in general, not only differential equation. I think that there is enough potential in Indonesia to consider a fuzzy like what we did already in Malaysia or Vietnam or other Thailand even. So I think that this university can start and make some progress in this way, and the students are frontier line and can develop good results. So in the postgraduate level, and so to see that also Indonesia in this field regarding the outputs of fuzzy, not only for differential equation, but also, for example, for neural network, machine learning, decision making, and so on. I hope that some students be interested to working on this concept and to have some interesting outputs from Indonesia in general, and especially from the Universitas Erlangga, so which I think that will be possible in the near future.
Yes, thank you. Yes, I guess that's correct. In our departments, there is no one who have interested or write research in this topic, just like fuzzy Reggie. Yeah. Okay.
Right.
So I guess we are in the end of today's lecture. I would like to say thank you to Dr. Ali Ahmadian,
Welcome.
especially for approving our proposal to become our academic fellow. We wish that we can have another collaboration later in the future. And for all the participants, thank you for participating in today's lecture. On behalf of the committee, I would like to say sorry for any technical problem. I hope to see you again next time. Okay, goodbye and wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. Have a nice day. Bye.
Thank you.
Thank you, Prof.
Thank you all. Thanks. Bye.